Okay, please someone confirm if it is audible. I'll just start the lecture. Okay. So, can anyone confirm here on YouTube if it is audible? I think it's audible. Fine. So, in the first two classes, we completed how to find the hybridization, how to find the formal charges on atoms. We also covered how to find the oxidation states, and we talked about covalent compounds, what are polar covalent compounds, what are non-polar covalent compounds, ionic compounds, and how to find whether how to find the extent of covalent character in ionic compounds using Fajans rules, and also how to find the extent of ionic character in covalent compounds depending on the dipole moments. Fine. And we have seen the structures of some molecules like water, hydronium, hydroxide, ammonia, ammonium, amide, and methane, carbocation, carbanion, carbon radical, etc. Okay, so today I will begin the topic of acid strength and basic strength, and we'll go to nomenclature individually whenever we go to subtopics. Like when we before starting alkanes, I'll go into the nomenclature of alkanes. Before starting ketones, I'll go into nomenclature of ketones, and before starting carboxylic acid, nomenclatures of carboxylic acids, and so on and so forth. Uh, but now we'll just stick with general organic chemistry. And before that, uh, let me just give you a quick revision of certain compounds, certain important cations and anions that you are supposed to know. Okay, so okay, you all know that halides are F minus, and I'm drawing the exact number of lone pairs that they possess: chloride, bromide, and iodide. So all of these contains 4 lone pairs, therefore 8 electrons, and therefore they they possess negative 1 charge. They have a charge of negative 1 because they are supposed to have 7, they have 8. Okay. Next, in here, see, the rule is this: whenever a halogen holds negative 1 charge, it has 0 bond pairs and 4 lone pairs. Okay, and whenever oxygen has 2 bond pairs and 2 lone pairs, whenever oxygen has 2 bond pairs and 2 lone pairs, it is neutral. Whenever it has 1 bond pair, when 1 lone pair and 3 bond pairs, it holds positive charge. And whenever oxygen has 3 lone pairs and 1 bond pair, it holds negative charge. So in this structure, if you see ClO minus, let me just highlight that. ClO minus, what do you think is the charge held by chlorine? Charge held by chlorine is 0. You know why? Because whenever halogens are attached to other halogens, for example, when you have elemental forms of halogens, you observe this thing. They all have 3 lone pairs and 1 bond pair. So number of electrons it has is 7. That's why it is neutral. So here also chlorine has 7 electrons and it is neutral. So here chlorine holds no charge. It is neutral because it has how many electrons? 1, 2, 3, 4, 5, 6, 7 electrons. Whereas oxygen here has 3 lone pairs and 1 bond pair, and always it has negative 1 charge. So this is called a hypochlorite ion. Okay, next. What about this? Cl is attached to 2 oxygens and one oxygen has a single bond between chlorine and oxygen. There is one single bond between chlorine and oxygen, and one has double bond. So whenever oxygen has 2 bonds, it will have 2 lone pairs and it will be neutral. Okay, and here chlorine has 3 bonds. So because there are 2 sigma bonds and 1 pi bond, so it will have 2 lone pairs. Now look at this. How many electrons does chlorine has? 1, 2, 3, 4, 5, 6, 7. That's why it's neutral. And here, how many electrons does oxygen have? Oxygen has 6. That's why that oxygen is also neutral. Whereas this oxygen has 1, 2, 3, 4, 5, 6, 7. So there is 1 electron extra. So you'll have negative charge here. Now what is this called? And this is ClO2 minus, this is ClO minus. This is hypochlorite and this is called chlorite. I'll tell you why the names are like this. This is called chlorite. Next. And I'll compare the structures also, don't worry. Next. If you have chlorine, which is attached to one oxygen with single bond. So whenever oxygen has one bond pair, it will have 3 lone pairs and it will have negative charge, and it is double bonded to one oxygen and this second oxygen, and there is 1 lone pair here. Now I will not go into detail here. This must be neutral. You should recognize by now this must be neutral because 2 lone pairs, 2 bond pairs. This must be neutral because 1, 2, 3, 4, 5, 6, 7. 7 electrons it is supposed to have, and it is having 7. That's why it's neutral. And this is negative 1 because oxygen, whenever it has single bond. Okay, anyway, I don't want to repeat it again and again. So this is called chlorate. This is called chlorate. And this is written by this form, this short form. This is the short form of chlorate. Fine. Next. There is one more structure that you need to know. Chlorine is double bonded to 3 oxygens and single bonded to 1 oxygen. So this will have 2 lone pairs each. Chlorine will have none because all are gone in bonding. So it has 1, 2, 3, 4, 5, 6, 7. This is neutral. This will have negative 1 charge. This is called perchlorate. This is called perchlorate. And the structure is ClO3 minus. So let us look at all the oxidation states of chlorine. Okay, in Cl minus, oxidation state of chlorine is -1. In Cl2 or ClCl, oxidation of chlorine is 0. And in ClO minus, oxidation state is +1. Okay, oxidation state is +1. In ClO2 minus, oxidation state is +3. I'll tell you why in a minute. And in ClO2, oxidation state is +5. I'm talking about oxidation state of chlorine. In ClO3 minus, oxidation state is +7. So oxidation state of chlorine can be -1, 0, +1, +3, +5, and +7. Now here oxidation state is -1 because it's simple. There is only one atom, and obviously, and it is having negative charge, negative 1 charge, so oxidation state is also -1. Here it is 0 because anyway chlorine is bonded to chlorine. So if you count everything, on chlorine, it will have 7 electrons on it. And while measuring oxidation state, you do partition such that more electronegativity atom gets all the atoms, but here on the side there is one more chlorine, so I should divide it equally. That's why it has 7. That's why oxidation state is 0. In ClO minus, so it is attached to this oxygen, and these are the lone pairs it has. Now when I do the partition of electrons, will I leave the electron with oxygen or chlorine? I'll leave the electrons with oxygen. You know why? Because oxygen is more electronegative. 3.5 versus 3.0. So it will get only 6. 1, 2, 3, 4, 5, 6. That's why it has 1 electron less. That's why oxidation state is +1. Here it is +1. Similarly here, when it is attached to 2 oxygens, one double bonded, one single bonded. Okay. So when I do the partition of electrons, who will get the electrons? Oxygen or chlorine? Oxygen, right? Because it is more electronegative. So how many electrons are with chlorine? 4. It is supposed to have what? 7. So it has having 3 less. So oxidation state is +3. Clear? And ClO2, similarly, if you do ClO2, for ClO2, let me go to ClO2. Cl is attached to, okay, this is ClO2. Let me go to ClO3. This is O3, sorry. This is O3. ClO3, it is attached to 2 oxygens with double bond, 1 oxygen with single bond, and 1 lone pair is left. And if I do the partition of electrons, all the electrons will go to oxygen because it is more electronegative. It has 2 electrons. It is supposed to have 7. It has 5 less. That's why oxidation state is +5. And for this also you can do. Oxidation state will be +7. Now, why the names? This is hypochlorite. This is chlorite. This is chlorate, and this is perchlorate. See, whenever you have lesser oxidation number, the names are ite, and whenever you have higher oxidation number, the names are ate. Okay, let me write again. ClO, ClO2, ClO3, and ClO4 all have -1 charge. Now, how to find the oxidation state directly? Oxygen always has -2 oxidation state. Oxygen always has oxidation state of -2. So it is overall having -1. So chlorine must have +1 because -2 + 1 is -1. Oxygen has -2, correct? So there are total 2 oxygens. Total it is having -4, correct? But overall it is -1. So -4 + 3 will give you -1. Now next, here there are 3 oxygens. Oxygen whenever is attached to other atoms will hold oxidation state of -2. There are total number of 3 oxygens here. So total -6 charge oxygen holds, but overall charge is -1. So what you need to add here? +5. Only then you will get what? Overall charge as -1. Okay. Next. Here you have ClO4. Every oxygen holds -2. Total 4 oxygens, -8. So what you need to add to -8 to get -1? You need to add +7. So the oxidation is +7, right? Okay. Now, whenever oxidation state is less, the names are ite. This is chlorite. This is whenever oxidation state is higher, the names are in the form of ate. This is chlorate. Okay. And if it is higher than chlorate, it is perchlorate, because higher means hyper, right? Hyper secretion, hyposecretion, you say. So higher is hyper. So this is perchlorate. And whenever something is less, you call it hyposecretion, right? Hyposecretion means if some hormone is secreted less than it should be secreted, you say hyposecretion. So here you say hypochlorite. Chlorite. It is less than chlorite. So name is hypochlorite. Now, if you form acid with this HOCl, whenever you have ite, you get us acid. So this is hypo. Let me write with, okay, I'll write it down because there is no space for writing names. So whenever you form acid with this, that means if H plus is attached to ClO, HClO, that forms hypo chlorous acid. Okay, and if it is HClO2, it is chlorous acid because it comes from chloride. So if it comes from hypochlorite, it is hypochlorous acid. If it comes from chloride, it is chlorous acid. And what about HClO3? HClO3 comes from chlorate, so it forms chloric acid. It is always ic. Us is always, whatever comes from it is always us. Whatever comes from it is always ic. So this is chloric acid. And what is HClO4? It is perchloric acid because it comes from perchlorate. Perchloric acid. Clear, fine. I'll give you some more names and then I'll continue with GOC. Okay, I'll give you some more important names of acids and ions and I'll continue. Everybody knows that H2SO4 is sulfuric acid and H2SO3 is sulfurous acid. Okay, some in some books you will find F, some books you will find PH. Okay, it's American and British English, so it doesn't matter. I'm just telling the names. And what about SO4 minus? SO4 2 minus. So whenever it loses 2 protons, this acid, you are left with SO4 2 minus, and here you are left with SO3 2 minus. So this is ic acid, that's why it is sulfate. So it is sulfate ion, this one, and this is called as sulfite ion. So always ic is related with 8 and us is related with it. Okay, let me give you two more examples. HN. Acha, what about oxidation states here? Here oxidation state of sulfur is +6 and here it will be +4. How to find oxidation state? It's very easy. Oxygen has -2, hydrogen has +1. Okay, whenever they are attached to other atoms. So oxygen, there are 4 oxygens, so it's total of -8 and this is +2, and if you combine it is -6, but overall it is neutral. So what you must add? +6. Here also this is +2 totally because two hydrogens, one each, and here 3 oxygens -2 each is -6. So -6 plus 2 is -4. To balance, to make it neutral, sulfur is supposed to have +4. That's why whenever oxidation state is less, it is called ite. Whenever oxidation state is more, it is called ate. If there is higher, you call it persulfate. If there is lower, you call it hyposulfite. But there is none that exists, freely. So we don't have anything like persulfate or hyposulfite, like in the case of chlorus and chlorite. Okay, sorry, in like in the case of chlorus and chloric. Okay, chlorus acid, you have perchloric acid, you have hypochlorous acid, but you don't have anything like hyposulfurous acid or persulfuric acid. Okay, next let us go to HNO3. This is called nitric acid. And HNO2 is called nitrous acid. And let me tell you, you can guess now what is NO3 minus called. This is called nitrite. Anything that corresponds, sorry, it is called nitrate. Anything that corresponds to ic acid is 8, and this is NO2 minus is nitrite. Anything that is associated with us is ite. Okay, and what about oxidation states? Here it will be +5 and here it will be +3. You know why? Because oxygen is -6, this is +1, total it is -5. To balance, to make it overall neutral, it should be +5. Here oxygen is -2, there are 2, so -4, this is +1, so overall it is -3. To balance it, what do you need? +3. Okay, that's why the oxidation state of nitrogen is +3 here, and so is here. Here also it is +3 and here it is +5. So this is a little bit about oxidation states of various structures, and if you want, you can look at the structures of sulfate, nitrate, and all, just like structures of ClO minus, ClO2 minus, ClO3 minus, ClO4 minus. You can just check it on the internet and you'll understand why. And you can use the method of finding formal charge and oxidation state to find the oxidation states the alternate way also. Anyway, let me go to acids and bases now. So acids and bases in organic chemistry. Okay. Now, any proton donor is an acid. In organic chemistry, primarily, whenever we say acid, we are talking about proton donors. Okay, and suppose hydrogen is attached to some uh, other group, it can lose a proton. It can lose a proton. That means this bond pair in between will be taken by the other part of the molecule, and here you are left with H plus. You know why? Because first this electron was with hydrogen, now it is losing that electron, so it has to get a positive charge, and A will gain that bond pair as a lone pair. And now initially A had one electron, now it has two electrons in the place of one electron. So one electron extra you are getting, so it will hold a negative charge. Okay. Now this Ha is acting like an acid. It is acting like an acid because it is a proton donor. Because any proton donor is called as acid, this is an acid for us. Now the reverse reaction is also possible. This lone pair can be donated to this proton, okay, and that lone pair will become bond pair, okay, and the reaction is coming in this direction. Now here this A minus, this A minus is acting like a proton acceptor. This is proton acceptor. This is acting like a proton donor. Okay. Now proton acceptor is called what? Proton acceptor is called a base. Proton acceptor is called a base. So what is the base here? This is base. This A minus is acting like a base. Now that base, you got it from this, right? When this was acting like an acid, after losing the proton, you got this. So we call these conjugate acid base pairs. Now here, which are conjugate acid base pairs? Let me write down again. Ha gives rise to H plus plus A minus. So which are conjugate acid base pairs? Ha and A minus are conjugate acid base pairs. Okay. Let me give you one example. Suppose you have water. Now water can act like an acid and donate a proton. So what will you get? HO. There were two lone pairs already, and this bond pair has become a lone pair. This bond pair has become a lone pair. So this green lone pair you get. Now it has negative 1 charge. Why? Because first it had only one electron here, now it has this electron also. So you have two electrons in place of one electron, so one extra electron you get, and you get a negative 1 charge. Now what is left here? H plus, because it is losing this red electron, so one electron is becoming less, so you got H plus. Now water is acting like what? It is acting like acid here. What is the conjugate base of water? Hydroxide. Hydroxide is conjugate base. Now this can act like a base. This can give this lone pair here and form back water. That means it can act like a proton acceptor. Okay, so hydroxide is a proton acceptor. That means it acts like a base and gives water. Now whenever acid forms a base, the base that forms after the acid loses H plus ion is called its conjugate base. And whenever base accepts a proton and forms an acid, the acid formed after the base accepts a proton is called its conjugate acid. Okay. One more example. Now water can not only act like an acid, but it can also act like a base. Let me tell you what I'm talking about. So this is your water molecule, and if there is a proton, or if the pH of water is less than 7, that means if water is acidic, okay, if there are so many protons in the vicinity, what can water do is, water can offer this lone pair to this proton and form a bond. So what will you get here? You will get oxygen. Okay, let me write in the same color. So you have oxygen, you have these two hydrogens, and one more new bond is formed here, and one lone pair remains as it is. Okay, so this new bond I'll write in yellow. So this new bond. So what will happen here? You'll get a positive charge because first it had two electrons. Now among those two electrons, among these two electrons were there, blue electrons. Only one electron is with oxygen now. One is with hydrogen. That's why it loses one electron and gains positive charge. Now here, what is water acting as? Water is acting like a base because it is accepting a proton. That means water can act like an acid as well as base. So that's why water is so important. Water can act like an acid, and water can act like a base because it can accept a proton and become hydronium. And what is this? This is the conjugate acid of water. Conjugate acid of water. Okay, that means water has what? Water has conjugate base and conjugate acid. Okay, let me draw it like this. So water has, this is OH minus, this is H3O plus. So this is conjugate base of water. This is conjugate acid of water. Now to form conjugate acid, water must act like a base. This must act like a base. To form base, this must act like an acid. That means water must act like an acid. Clear? Fine. Now let me come to some other example. No, before going into any other example, let me tell you one thing. Whenever I write an acid base equation, H2O, sorry, H2O is in equilibrium with H O minus plus H plus. I write this equilibrium sign in between, this equilibrium sign. Okay. This equilibrium sign. What does equilibrium signify? That means reaction can go in the forward direction or it can come in the backward direction. Now the thing is where the equilibrium lies. The question is where the equilibrium lies. Does equilibrium lie to the left or the equilibrium lie to the right? If the equilibrium is inclining towards right, it is a strong acid. That means it is very easily giving or donating a proton. If the equilibrium lies towards left, that means this molecule is, you know, this molecule is preferring to stay as it is. That means it is not willing to donate a proton very easily. Then that acid is what? Weak acid. If it is willing to donate the proton very easily, it is eager to give proton very much, it is very eager, then it is a strong acid. That means if the equilibrium is more towards right, more acidic the compound on the left is. If the equilibrium is more towards left, then less acidic the compound on the left is. Clear? Now, how to measure the strengths of acid? How to measure the strengths of acid? Let's just check. Now, I'll compare certain acids here. Suppose you have HF, HCl, HBr, and HI. Now, if I am writing the equations, let me write. I am writing H plus F minus. So here we had 3 lone pairs. Here we have 4 lone pairs. So what is happening here? This is taking away the bond pair as a lone pair. So here we had 1, 2, 3, 4, 5, 6, and this will be in equilibrium with H plus Cl minus. What about this? Again, this will grab this. It had, so it will H plus Br minus. Here it will have 4 lone pairs. What about this? It has 3 lone pairs here. This bond pair will become lone pair, and you'll have this. Now the question is, which is the strongest acid among all these? All these are acids, right? HF is acid, HCl is acid, HBr is acid, HI is acid. Why they are acids? Because they are all donating proton. They are all donating protons. Now the question is, which is the most acidic among these? Now how to answer this? Now the equilibrium will lie towards right. It will lie towards right if the compounds on the right are stable. That means if F minus is stable, equilibrium will lie towards right. If it is unstable, then equilibrium will lie towards left. Okay, that means among these, whichever is the most stable will have the equilibrium most towards right. That means it is most acidic. So in other words, these are the conjugate bases, right? These are the conjugate bases. F minus is the conjugate base of HF, Cl minus is the conjugate base of HCl, Br minus is the conjugate base of HBr, and I minus is the conjugate base of HI. Now more stable the conjugate base is, more willingly the acid will donate the proton. Clear? Stabler the base, more towards right the equilibrium is. More towards right the equilibrium is, in other words, more willing the acid is to donate the proton. That means if conjugate base is happy, the acid is happy to give away the proton, because conjugate base is, stable, happy and stable. Now the question is, which among these is most happy? F minus, Cl minus, Br minus, or I minus? So let us try to understand that. Now we are comparing all the acids down the group. Okay, these all belong to one group: fluorine, chlorine, bromine, and iodine. Now F minus is something like this. Cl minus is something like this. It is little bit bigger. Br minus is much larger, and I minus is the largest. The thing is, every one of them has -1 charge. The charges are equal everywhere, but the charge is dispersed in larger volume in case of I minus, and the charge is very concentrated, or is concentrated in the smaller volume in case of F minus. So which is most reactive? This is most reactive, right? Because charge is, this is most reactive, because the charge is concentrated in smaller volume. Which is least reactive? This is least reactive. Why? Because charge is dispersed. Now tell me, which is more stable, this or this? I minus is more stable. So which will be more willing to go to the right? HI. Which is the least among these to go to the right? Least willing? HF. So the acid strength, if you see, if you look at the acid strengths of these HF, HCl, HBr, and HI, the acid strength of HI is highest, then it is HBr, then it is HCl, and the least is HF. The least is HF. And generally speaking, HF is considered as a weak acid. Generally, when you go to lab, you say that HF is a weak acid. That means it doesn't, almost dissociate totally. Whereas HI dissociates almost. That means the equilibrium constant is very, very, very high. Okay, concentration of products by concentration of reactants is a very big number. Whereas if you take out the equilibrium constant for HF, it is a small number, not very, very large. It's not like 10 power 10 or 10 power 9 or 10 power 30 or something like that. It is a small number. Anyway, let us now we have compared the acid strengths of acids down the group. Down the group. See down the group HF, HCl, HBr, and HI. So this is most acidic and this is least acidic. The reason was the conjugate bases, you know, were of different stability. The conjugate base I minus was the most stable because it was the largest, and negative charge was dispersed over a large volume. That's why it is not very reactive. Whereas F minus is small. F minus is small, and the negative charge is concentrated in the smaller volume. That's why it's more reactive. This is very important. Acid strength is always measured based on the stability of the conjugate base. Acid strength is always measured based on the stability of conjugate base. Now let me go to the next comparison. The comparison of acid strengths of acid across the group. Okay, not down the, so across the period, not down the group, across the period. Let me tell you what. Let me write down. This is CH4. So whenever I say acid, I'm talking about proton donation. So I'll just take the compounds which have hydrogens attached to it because I need to donate a proton. Then comes NH3. Then comes NH3. Then comes H2O. Then comes H2O. Then comes HF. Now look at a sequence here. Look at a pattern here. The pattern is this: 4 bond pairs, 0 lone pairs, 3 bond pairs, 1 lone pair, 2 bond pairs, 2 lone pairs, 3 lone pairs, 1 bond pair. Okay. So if I write bond pairs and lone pairs, I'm just revising these things. So bond pair 0, no, not 0, 4. 4 bond pairs, 3 bond pairs, 2 bond pairs, 1 bond pair. Lone pair 0 lone pair, 1 lone pair, 2 lone pairs, and 3 lone pairs. Anyway, we are not talking about this here now, but anyway, I'm just reminding you. Now, if I want to compare the acid strengths here, so let me write down quickly. CH3H, I'm just writing the short form. So when it is acting like acid, it will take away this bond pair, and what will be left here? H3C minus plus H plus. Okay, next NH2H. So just I'm writing this in a different style in the shortcut because I don't want to draw all the structure. So when it acts like an acid, it will grab this bond pair, and what is left? 2 lone pairs with negative charge. H2 I can write. So this is amide plus H plus. Now what about water? Water, if I write OH H. Now if it acts like an acid, then it is OH minus hydroxide plus H plus. Correct? Next. Last is HF. HF, if I write, I'm writing FH. It doesn't matter. FH or HF, it is same. Now if fluorine grabs this bond pair, what is left? F minus plus H plus. Now tell me, which is more stable? Now here I am not interested in size. See, down the group we were looking at sizes. Down the group we were looking at sizes of fluorine, chlorine, bromine, iodine, because size changed significantly from one period to another period. Now down the group you are increasing 1 period each. That means you are adding 1 extra orbit when you come from 1 period to the second period, right? Down the group. So increase in size of the atom or ion is very significant. That's why here size was the criteria. When you are comparing acids down the group, size was criteria. But when you are comparing acids across a period, so the period is same, so the number of orbits are also same, so sizes will not change significantly. Size of carbon, nitrogen, oxygen, and fluorine is almost of same range. Okay, it decreases, that is a different thing, but it doesn't decrease significantly. That's not the important factor. What important factor is, what important here is, what is important here is the electronegativity. So electronegativity of carbon is 2.5, electronegativity of nitrogen is 3.0, oxygen is 3.5, and fluorine is 4.0. Now, more the electronegative element, more the electronegativity, electronegativity, happier the atom or ion, whatever it, atom or ion is with negative charge. Okay, that means who is the happiest here among all these? Fluorine is the happiest with the negative 1 charge. Least happy is carbon because it is not very electronegative and it doesn't like negative charge. Electronegative elements like negative charge. Less electronegative elements don't like negative charge. So fluorine is the happiest. If fluorine is the happiest, this is the most stable. Most stable. And if carbon is least happy, it is least stable. Now, if stable, if more stable, if the conjugate base is stable, if the conjugate base is stable, the equilibrium is towards right. Okay, stabler the conjugate base, more towards right the equilibrium is. Stabler the conjugate base, more towards right the equilibrium is. Now tell me which equilibrium is most towards right? The last equation. In the last equation, equilibrium is most towards right because F minus is most stable. In which reaction or chemical equilibrium it is least towards right? In the first reaction, because carbon is not happy with the negative charge. Now tell me, among this, what is the ranking of acid strength? So what are we comparing? We are comparing CH4 with NH3, which with what? With what? Water and last HF. We are comparing these. So if I compare the acid strengths, the most or the highest acid strength belongs to HF, then H2O, then NH3, then CH4. What was the reason I gave? Reason was electronegativity. So this was 4.0, 3.5, 3.0 and 2.5. Okay, and one more thing. What was the conjugate base here? It was CH3 minus. Here it was amide, NH2 minus with 2 lone pairs, and here it was hydroxide with 3 lone pairs, and here it was fluoride with 4 lone pairs. Now, which is the most stable here? This is the most stable. This is the least stable. Now, most stable is what? Least reactive. That means this is, wait, that means this is most stable, least reactive, so it is weakest base. This is strongest base. Now if I consider the basic strength of this is highest, second highest is amide, then comes hydroxide, then comes fluoride. So what do you conclude here? A strong, I'll write down, a strong acid has a weak conjugate base, and a weak acid has a strong conjugate base. Clear? See, I'll just write down the acids and conjugate base. Again, HF, HCl, HBr and HI. F minus, Cl minus, Br minus and I minus. Now, strongest acid, weakest acid. No. Weakest acid, strongest acid. Strongest base. So strongest means what? Among the given bases, this is the strongest base. This is the weakest base. Let me write down one more set here. CH4, NH3, H2O, and HF. Among this, this was the weakest acid, and this was the strongest acid. Let me write down the conjugate bases. CH3 minus, NH2 minus 2 lone pairs, OH minus 3 lone pairs, and F minus 4 lone pairs. Here I didn't write lone pairs, but okay, it's okay. So let me take another color here. So weakest acid has strongest conjugate base. So this is strongest base. Among these, this is the weakest base. Clear? Okay, that is fine. Now what did we see here? Now whenever you are comparing something down the group, you always go to the size. Okay, here you always go to the size and then decide which conjugate base is weakest or most stable. So whichever is most stable, the acid corresponding to that is most your or the acid corresponding to that has the highest acid strength. Okay, whichever base or conjugate base is the strongest or most unstable, the acid corresponding to that conjugate base is weakest. Okay, and here you looked at the stability of conjugate bases by looking at the sizes of the conjugate bases. Why? Because these are all of different sizes. The larger the size, more dispersed the negative charge and more stable the anion is. So I minus was the most stable. That's why Hi was very happily giving away proton. Okay, because iodine is happy without proton, and fluorine is not that happy without proton because the size is small, and because of the small size, the concentration of charge is more, and it is more reactive. More reactive means less happy. But here, when you are looking at the acids across a period, you are not comparing the sizes, because sizes are almost same in a period because number of shells are same. There is only small insignificant change in size. So I'm not looking at the size, I'm looking at the electronegativities. So whichever has the highest electronegativity is comparatively more happy with the negative charge. Now here fluorine has the highest electronegativity. That's why what? It is the happiest. That's why HF was leaving proton easily compared to all other three acids here. Now which was the least happy with negative charge? Carbon. That's why it doesn't give proton. Alkanes don't give protons. Okay, you don't come across carbanion very much in organic chemistry as much as carbocation, because carbon is not very electronegative element. That means it can bear positive charge, comparatively uh, more happily. uh, you know when you compare, if you compare negative charge on carbon and positive charge on carbon, carbon will prefer positive charge. That's why you come across carbocation very much in organic chemistry, but carbanion you come only in rare cases. Okay, for example, in Grignard's reagent you come across carbanion, and in iodoform reaction carbon gets negative charge, but apart from these reactions you never come across carbanion. Anyway, let's proceed to the next comparison of acid strengths. Let me compare these compounds. This is ethane. What is ethane? H3C bonded to H2, and there is one more hydrogen, but I am drawing separately because I want to look at its acid strength. And then ethene or ethylene, which is CH2CH2, but I am drawing this separately. Then comes acetylene. So acetylene is CH triple bonded to CH. So I'm drawing H down just to compare all three. Now when the first thing acts like acid, this bond goes here. When the second thing acts like acid, this bond goes here. When third thing acts like acid, this bond goes here. So this is in equilibrium with something, this is in equilibrium with something, this is in equilibrium with something. Now here you get what is the conjugate base you get here? H3C single bond CH2 and a lone pair with negative charge. Here what do you get? H2C double bonded to C H, a lone pair here. What do you get here? HC triple bonded to C and a lone pair here. Okay. Now plus H plus. Okay, I'll write in some other color because it will look complicated otherwise. So let me take this. Okay. Plus H plus plus H plus plus H plus. Now this is the conjugate base of this. This is the conjugate base of this. This is the conjugate base of this. Clear? Okay. Now, which conjugate base is more stable? Is this more stable? Or is this more stable? Or is this more stable? That is the question. Now, whichever has the most stable conjugate base, the acid corresponding to that is most acidic. Okay, because if conjugate base is stable, it is happily giving away the proton, or it is living happily without proton. That's why it is giving away proton. And more it gives proton, more acidic it is by definition. Now let me compare whether this is more stable, this is more stable, or this is more stable. I claim that this is most stable, this is most stable, and this is least stable. This is least stable. I'll tell you why. In the third case, see, this carbon is what? How many groups are attached to this carbon? H, C, triple bond C, and there is one lone pair here after it lost proton. How many groups are attached? One lone pair and one sigma bond. I told you never to count pi bonds while looking at hybridization. So here hybridization is what? Sp. Here hybridization is Sp. Next. What about this? H2C double bond C, there is one H and there is one lone pair. What is hybridization here? Now count how many groups are attached. One lone pair, one sigma bond here, one sigma bond here. I don't count pi bonds, so there are three groups attached. That's why it is sp2. Next, let us look at the conjugate base of ethane. H3C single bond H, and there are two hydrogens attached. One hydrogen is lost as proton, so this lone pair remains. So let me count how many groups are there. One lone pair, one sigma bond, two sigma bond, and three sigma bond. Three sigma bonds and one lone pair. So there are four groups. That's why it is sp3 hybridized. Now I told you already, when you have sp hybridization, the orbital is short. In sp2 orbital is little bit long, and in sp3 the orbital is longest. Orbital is longest. Now what is the why is it so? Here p character is more. Here p character is less. That's why it is short. Now tell me, in which case the electrons are held close to the nucleus, in sp or in sp3? The answer is in sp electrons are closer to nucleus. Closer to nucleus. You know why? Because nucleus is here, the electrons are in this region. That's why they are closer to nucleus. And here p character is more, the orbital is long. That's why electrons are farther from nucleus. Okay, electrons are farther from nucleus. So if electrons are far, they are out of the control of this nucleus, and they will react with the neighboring nuclei. That is nothing but what? It is more reactive. This is most reactive among three. Why? Because sp3 most reactive. sp3 orbital is long, so the electrons are more away from the nucleus and they react with the other nuclei. That means, in other words, they try to grab proton more. But here electrons are closer to the nucleus, so they are in control of this nucleus, and comparatively they don't try to grab H plus as much as this. So this is trying to grab H plus the most, this is trying to grab H plus the least, and this will come in the intermediate. Okay, this is the intermediate of these two. Anyway, so which reaction will go backward most? This. You know why? First reaction. You know why? Because this is most reactive, because this is long and it is reacting with H plus the most, and this is not very backward. That's why I'm that very desperate to go backward. That's why I'm drawing a smaller arrow. Why? Because this is short and it is not very much reacting with H plus as compared to this. Okay, now third criteria is, see, in the first case what did we do? When we looked at HF, HCl, HBr, HI, we compared the sizes. Then we compare the electronegativities. Okay. Now here everything is carbon, right? All three cases we have carbon. So neither size is different nor electronegativities are different. In fact, carbon is same. So here we are comparing hybridizations. We are comparing hybridization. So three factors we have seen: sizes, electronegativities, and hybridization. Now there is one factor that is far more important than, you know, uh, hybridization, and after that there is, I'll tell you, there is one very important thing called aromaticity also. I'll go to that later, but before that I'll just go into resonance and I will compare the acid strengths of some acids. And then when I discuss aromaticity, I will tell you why aromaticity overrides all other factors. I'll tell you why: because anti-aromatic compounds are very unstable and aromatic compounds are very stable. There is exceptional stability for aromatic compounds and there is exceptional instability for anti-aromatic compounds, but I'll come to that later. But before that, let us just discuss hybrid, resonance. Now everybody may be having, some idea about resonance. Now what happens in resonance is there is delocalization of electrons through conjugation. I'll give you one example. If you have ethyl alcohol, CH3, CH2, OH, it can act like acid. How can it act like acid? So I'll just draw structure like this, OH. So this bond pair can become lone pair. And what do you get? Ethoxide. This is O, and instead of two lone pairs, now we have three lone pairs. That's why we get negative charge plus proton. Now this ethanol is acting like an acid because it is donating a proton. Fine, well and good. I'll draw one more structure, which is structure of acetic acid. This is acetic acid. I'll draw in little bit detail. So this hydrogen I'll draw with a bond. Okay, just to show clearly. Okay. So what happens here? Here we have two lone pairs. Here you have two lone pairs. This bond pair will become lone pair now. And what do you have? CH3, C, double bond O. And then here O has negative charge plus H plus. Now acetic acid is also acting like an acid. The name itself is acid, acetic acid. Okay, it is acting like an acid. But the question is this: which is more having more acid strength, uh, ethyl alcohol or acetic acid? Which among these two is having more acid strength? Now everybody can guess that acetic acid has more acid strength because its name itself is acid. Okay, that is guessing with the name. But what is the logical reason behind why acid strength of acetic acid is more compared to ethanol? Let us try to understand. Now you look at conjugate bases. Now focus on conjugate bases. I told you, if conjugate base is stable, then the corresponding acid from which you got the conjugate base is more acidic. Now if this is more stable, this will be more acidic. But if this is more stable, this will be more acidic. Now how to check which is more stable? I claim that the second acetate, this is called acetate, the conjugate base of acetic acid is called acetate ion, and conjugate base of ethanol is called ethoxide. The name itself is ethoxide, okay, because ethyl group is attached to oxygen, that's why it is ethoxide. Now I claim that acetate is more stable than ethoxide. I'll tell you the reason why. If you look at ethoxide, the negative charge is on oxygen. Who is taking the responsibility of negative charge? Oxygen is taking the responsibility of negative charge. Whereas in acetate also the negative charge is on oxygen, but this can undergo resonance. What is the meaning of resonance? This lone pair can become bond pair here, but if this becomes bond pair, carbon will have 5 bonds, but carbon never has 5 bonds, it has only 4 bonds, so it has to break this pi bond and send it to oxygen as a lone pair. Okay, this is called resonance. That means, see, resonance is written like this with double arrow. It is not an equilibrium. The thing is, the structure is the average of these two structures. The second structure that I am going to draw, you will understand what the structure is. So CH3, I'll discuss about resonance later in detail. Don't worry. So this becomes a lone pair, and this will be negative charge. See, I told you, whenever oxygen has 1 bond and 3 lone pairs, it has negative charge, and this will become double bond, and oxygen will have only 2 lone pairs now, because 1 lone pair became the pi bond, and this will become neutral, because whenever oxygen has 2 bond pairs and 2 lone pairs, it is neutral. Now, see what is happening. The structure is actually average of these two structures. Okay, what is the meaning of average of these two structures? The negative charge is shared by this oxygen and this oxygen. That means this oxygen and this oxygen are sharing the negative charge. That means in acetate, the negative charge is here sometimes and it is here, not sometimes, actually it is actually half. It is average of these two. So in case of acetate, negative charge is what? Distributed over these two oxygens, and here it is fixed on this oxygen. We call it localization and delocalization. Here the negative charge is localized, and here the negative charge is delocalized. Whenever negative charge is localized, it is concentrated at that center, and that's why that part, or that center where the negative charge is concentrated, is more reactive towards H plus. So because here negative charge is concentrated, it will very reactively grab the proton back and go in the backward direction. If it is going in the backward direction, this is not very acidic. But here, because the negative charge is distributed or diluted or delocalized, it will not react with this H plus as much, as ethoxide. That means it is comparatively more stable. If it is comparatively more stable, the reaction will not be backward that much. That's why I'm drawing a smaller arrow. Okay, that means this is more acidic. That means it will prefer to stay like this. That means what? When you compare ethoxide, ethanol, CH3CH2OH with CH3COOH, this is more, okay, not, I should not say acidic, it is having more acid strength. This is having, this is having lesser acid strength comparatively. What was the reason? The conjugate base of ethanol was CH3CH2O minus, or ethoxide. The conjugate base of this, I'm drawing the detailed structure, was this CH3COO minus. So this is the detailed structure. Now here there is delocalization or resonance. Delocalization means this can come here and this can come there. So what was happening? I'm drawing the structure again after resonance. This will become single bond, this will become 3 lone pairs, this will become double bond. So this will become neutral. Now this negative charge is shared by these two oxygens, this oxygen and this oxygen. See here, when I'm highlighting or denoting by green color, the negative charge was with the oxygen on the bottom, but in case of blue color, the negative charge was with the oxygen on the top. That means the negative charge is being shared by these two oxygens. That means negative charge is delocalized here. If negative charge is delocalized, it loses its intensity or concentration or reactivity, which makes acetate more stable. That means acetate is a weak conjugate base. So the acid corresponding to that, or the conjugate base of this will be, sorry, conjugate acid of this will be more acidic. That's why CH3COH is more acidic or having more acid strength compared to what? Compared to ethanol. Now let me compare one more. Three things. I'll compare three things. I'll compare three things. So I'm comparing ethanol, acetic acid, and phenol. Phenol has a benzene ring, and on benzene ring you have OH. This is called phenol. Now what is the conjugate base of ethanol? We just wrote CH3 CH2O minus. This is the conjugate base, and here it is CH3. I'll write in detail COO minus. This is the conjugate base. And what is the conjugate base of phenol? It's this. After losing proton, this will be the conjugate base. So I'm writing the equation here. This is okay. This is in equilibrium with this. This is in equilibrium with this. This is in equilibrium with this. And here you have H plus. Here you have plus H plus. And here you have plus H plus. Now this is localized. Here negative charge is localized. If it is localized, it is very reactive because it is concentrated at one single center. So that's why it is least stable. Here it is delocalized, we just saw. Here also it is delocalized. I'll just illustrate that, or I'll just write down the resonance and I'll tell you why it is delocalized. If I draw the structure of phenoxide, this is negative charge, and if it comes here, this comes here. So this becomes double bond and it will become neutral oxygen. And here this, sorry, let me draw. This bond will become, this sigma bond will become, this sigma bond will be, let me write. Yeah, this pi bond will become lone pair here. So I'll get a lone pair here. This pi bond is like that, this pi bond is like this, same. It is not disturbed. Okay, now again, this can become a pi bond here and this can become a lone pair here. So this comes here, this becomes a pi bond, this pi bond remains, and these two bonds remain like this. Now this can come, I'll write in some other color. So this lone pair can come here, and here this will become, sorry, this lone pair will become pi bond and this pi bond will become lone pair. So what will you get? You'll get this. This will become pi bond. Here you'll have negative charge with lone pair, and this will be as it is. And again this can come here and it can come back. Okay, whatever it is, the negative charge is what? Moving. It is on oxygen here. Here it is on this carbon. Here it is on the carbon at the bottom. Here it is carbon at the northwest direction. Here it is in northeast direction. Here it is in northwest direction. Here it is in south, and here it is on oxygen. So basically the negative charge is shared by, what? In phenoxide, negative charge is shared by, let me draw, this oxygen, this carbon, and this carbon. All the resonance structures say. So the negative charge is delocalized here. Let me come back to the, here. Then here negative charge is delocalized here, and it is delocalized at this carbon, at this carbon, at this carbon, at this carbon and at this carbon, and this oxygen. 3 carbons and 1 oxygen. Now the question is, which is more stable? Is acetate more stable or phenoxide more stable? The answer is, surprisingly, acetate is more stable, even though it has only 2 resonance structures. Okay, only two contributing structures in resonance for what? Acetate. There are 4 contributing structures in resonance for phenoxide, but still acetate is more stable. I will explain why. There are 2 reasons. When you study resonance, they say that if 2 resonance structures are similar, CH3, CO, O minus, and it is in resonance with this CH3, C, the negative charge will come to the oxygen at top, this will become double bond. So these are the 2 resonance structures. 2 resonance structures are similar, resonance is strong. If 2 resonance structures are similar, see, these 2 are similar structures almost. They are symmetric. This and this are symmetric. Okay. So resonance is strong. Second reason is, in case of phenoxide, the negative charge is shared by 1 oxygen, 3 carbons. And here in case of acetate, it is shared by, negative charge is shared by 2 oxygens. And I already told you, oxygen has electronegativity of 3.5 and carbon has electronegativity of 2.5. Okay. Now carbon doesn't like negative charge. I told you already, carbon hates negative charge because it is not an electronegative element. Only fluorine and oxygen like negative charge, and halogens like negative charges. Okay. Now here, is it better or is it more stable if negative charge is shared by 2 oxygens, or is it more favorable if negative charge is shared by 1 oxygen and 3 carbons? It is better that negative charge is shared by 2 oxygen. That is more stable. Okay. That means who is stable? Acetate or phenoxide? Acetate is more stable. If acetate is more stable, see, acetate is more stable, and this ethoxide is least stable because there is no resonance at all. Correct? At least in phenoxide we at least have some resonance. That makes it more stable than ethoxide. So the stability of this is intermediate compared to acetate and ethoxide. So which is the most having the most acid strength? This is having the most acid strength. Least acid strength. And this has intermediate acid strength. This has intermediate acid strength. I'll show you the pK. I'll tell you what pK values are first, and then I'll show you a table that has pK values of various compounds, where you can compare acid strengths of various acids. Okay. Anyway, now if I want to write the acid strengths of if I want to compare acid strengths, so CH3 COOH is having more acid strength than phenol. Okay, this is having more acid strength than phenol, and phenol has more acid strength compared to ethanol. Clear? So this is the comparison. Now let me go to next topic, in which we study electronic effects. Okay, 1 second, it's not visible. Okay, I'll just reconnect it. Yeah, I think it's visible now, right? Okay, fine. I'm I'm just continuing here. Okay. Now I'll draw an alcohol. I'll draw an alcohol. It is a alcohol with this long chain. Some alcohol. Okay. If I see one carbon, two carbons, three carbons, four carbons, and five. This is a molecule of pentanol. Okay. This is molecule of pentanol. Okay. Just let me come back. Yeah. Okay. This is a molecule of pentanol. Now I'm drawing some derivatives of pentanols. Okay. Just let me draw one more. Let me draw one more. Now here I have fluorine attached to this. I have fluorine attached here, and I have fluorine attached here. Now the question is which is more acidic now, or which is having more acid strength. Whenever he is asking about acid strength, I told you that first thing we need to check is check the stability of conjugate base. What is the conjugate base here? It is O minus. This is the conjugate base, right? So the first conjugate base is this. The second conjugate base is this, and for this fluorine is attached here, and the third conjugate base is this, and here fluorine is attached here. Okay, so these are the various conjugate bases, corresponding conjugate bases. Now tell me which is more stable. This is most stable, and this is least stable. I'll tell you why. Fluorine is what? Fluorine is an electronegative element, and it pulls away the electrons. It pulls electrons from everyone. Now, what is the reason for the reactivity of this conjugate base? The negative charge on this oxygen, right? Now, because it is more electronegative, it will pull a little bit of negative charge from this, and it will reduce the intensity of negative charge here, which is the reason why it reacts. That means what? It will make it more stable. If it makes it more stable, it is weak conjugate base. If it is weak conjugate base, the conjugate acid is what? The acid corresponding to it is what? Strongest. That means this will more easily give you the proton because this is more stable. Here fluorine is far, that's why it cannot pull away electrons as much as fluorine in the neighborhood. Okay, I'll tell you why. And this effect is called minus I effect or negative inductive effect. Negative inductive effect. Now inductive effect falls significantly with distance. Inductive effect falls significantly with distance. I'll tell you why. Why? Because I'll tell you. If you have a long molecule and if you have fluorine attached here, okay. I'll just reconnect it. So I'll just try to reconnect it. It's just disconnected. Okay. Okay, anyway, I think it's 1.5 hour almost. So till now we discussed about certain aspects of acid strength. Tomorrow I will continue with the factors that affect acid strengths of various molecules, like inductive effect, mesomeric effect, and then I will go to basic strength. I'll go to basic strength, and there also we will see how various factors affect basic strengths of compounds and how basic strengths compare to each other. Basic strengths compare to each other. And then at last I will introduce you to a very important topic called aromaticity, which are aromatic compounds, which are non-aromatic compounds, which are anti-aromatic compounds, and based on that how the acid strengths and basic strengths changes, or the ranks or orders of acid strengths and basic strengths changes. Okay, fine. Anyway, I'll end the lecture now, and then we'll start the lecture tomorrow. Not tomorrow, Sunday I'm not taking any lecture. We'll continue with the lectures on Monday. Okay, so now I'll end up the stream. Thanks for watching. We'll meet in the next session. Thank you.